Hello everyone. In today's video, I will walk you through how to simulate a grid farming system featuring two parallel inverters operating in load sharing mode. First of all, let's break down the structure of a single inverter. This one. As you can see, it consists a control block, a three-phase inverter, and a three-phase LCL filter. Now let's look inside the controller. This is the inside the controller. Here we have the inner loops, the PWM modulation, virtual impedance, and the power measurement and group control. I want to emphasize the virtual impedance because this component is critical. Without it, the two inverters will not be able to share the load equally. And you can compare the theoretical diagram with the this simulink model to follow along more easily. This is the, this is inside the Droop controller. This is the voltage controller. This is virtual impedance. I put the virtual impedance block inside the voltage controller, and the last one is current controller. This is the detailed sketch in current controller. Current controller. Finally, inside the controller subsystem, I will open up the blocks so you can see the exact parameters I've turned for the PI controllers and other blocks. Here, this is the general structure of the grid forming inverters. I go inside one of them and go inside the grid forming controller. Inside the Droop controller, as I said, and this is active power reference. This is the step time. This is the amplitude multiplied to 1000. This is the first order filter. And the frequency here is 50. This is a three-phase power measurement. This is a reactive power reference. This is the two gain of the Droop control. This is the Vmax. This is the you can see the frequency 50 here. This is omega. And inside the voltage controller, this is virtual impedance. This is PI controller in voltage controller. KB, KI, and the same as the under PI controller block, PI, KB, KI. This is the value of the capacitor in LCL filter. And this is the current controller. Similarly, KBKI of the current controller. This is the value of inductance in LCL filter, LC. This is PWM modulation. The frequency here is 15 kilohertz. And this is the H three-phase bridge inverter. This is the three-phase VI measurement. This is a LCL filter, three-phase LCL filter. LCL. And this is for the Graphic inverter 1, and in Graphic inverter 2, they are the same. But inside the Graphic controller, and look at the virtual impedance. This is RV2, XV2, XV2, RV2. It's not RV1 like the inside the reforming controller 2, 1. Sorry. I forgot to change the name here, but it is actually reforming controller 2 because I copied the reforming inverter 1 and paste to the reforming inverter 2. And I also changed the name 1 to 2. As you can see here, it's 2 to 2, no 1. B reference and Q reference. The difference between the grid forming inverter 1 and grid forming inverter 2 are the these ones and this one. Yeah. Yeah. All right. And for the next part is transmission lines. You know, the value of resistor and inductance R2 and L2 is 20% higher than the value of that in line 1. For the load, and for the load, and it depends on the switching time 0.5, 1 and 1.5. Now, at the time 0.5, the three-phase breaker here will closed, and and the total load is 12 plus A equal to 20 kilowatt, and the total reactive power is 4. And when at the time 1 second, the three-phase breaker would open, and the actual load at this time is equal to load 1, and at the time 1.5 second, the three-phase breaker you know close again, and the load at this time equal to load 1 plus load 2. And how to calculate the parameters in LCL filter. I'll show you. This is some these are some formulas to calculate the LCL filter, as you can see, and I also added in the code to the code. And this is this is how to calculate LCL filter, as you can see, and some initial parameter I also showed to you at the beginning of the code. This is the PQ reference. Sorry, PQ rate. This is the maximum power, reactive power, and active power per inverter. This is these are two formulas to calculate the PF Droop coefficient and QV Droop coefficient. This is the value of transmission line 1 and transmission line 2. And this is the value of virtual impedance. And then let's go to the result. When the system has Droop controller and virtual impedance block, as you can see, let's look at the current sharing. For the current sharing, two waveform are virtually overlapped. This is a crucial result. It proves that the Droop control not only sharing the load equally, but it also successfully compensating for the impedance of the transmission lines. The current amplitude directly reflects the total load demand at the time t equal to 0.5 and t equal to 1.5. Both branches equally increase their current output to meet the total 20 kilowatt. As you can see here. And at the time 1 second, both branches equally decrease their current at the total load droops back to 12 kilowatt, and uh, for the PF Droop control response, um, this is F, this is PF. As you can see, at the time t equal to 0.5, the load increase, and you can see a sharp frequency dip occurs. Then it returns to 50 hertz. And at the time 1 second, at this time, the load decreases. Inversely, a sharp frequency spike occurs. Then it returns to 50 hertz. And at the time 1.5 second, the 0.5 event is repeated, as you can see. And for QV Droop control response, this is QV. You can see at the time 0.5 second, the Q load increases, and you can see a sharp voltage dip occurs, and the system stabilizes at a lower voltage to supply the higher reactive power. And inversely, at the time 1 second, reactive power decreases and a sharp voltage spike occurs right here. The system stabilizes back at the original voltage. You know, higher voltage for the lower reactive power. At the time 1.5 second, it is the same as the time 0.5 second. And for the active and reactive power sharing, as you can see here, for the reactive power, both inverters share the load, the total load equally. You know, you can see the two waveforms are overlapped, and similarly, the reactive power also the reactive power of these two inverters also overlapped. Both inverters share the total reactive power, as you can see. And I have a question: what if the system does not use Droop control? I also initially I also designed a two inverter system which doesn't contain contain Droop control and virtual impedance. Let's see what happened. For the current sharing. Okay, I forgot to click the run button here. and you can see the magnitude of the inverter, the current in inverter 1 is over 20, but on the other hand, the magnitude of the current passed through the inverter 2 is under 20. So the the so in conclusion, the magnitude of three currents here is are not equal. And for more clearly, you can see the active and reactive power relationship for the uh, for the active power. P1 is much higher than P2, and similarly Q1 is much higher than Q2 because of the transmission line. Transmission line 2 is higher than transmission line 1, so the power of inverter 2 will would be lower than the power of inverter 1. Yeah, and that's it. Thank you for your watching and for your listening.